Feynman's algorithm. While at Los Alamos National Laboratory working on the Manhattan Project, Richard Feynman developed a bit processing algorithm to compute the logarithm that is similar to long division and was later used in the connection machine. The algorithm relies on the fact that every real number x where 1 less than x less than 2 can be represented as a product of distinct factors of the form 1 plus 2 minus k. The algorithm sequentially builds that product p, starting with p equals 1 and k equals 1. If p 1 plus 2 minus k less than x, then it changes p to p 1 plus 2 minus k. It then increases by 1 regardless. The algorithm stops when k is large enough to give the desired accuracy. Because log x is the sum of the terms of the form log 1 plus 2 minus k corresponding to those k for which the factor 1 plus 2 minus k was included in the product p, log x may be computed by simple addition, using a table of log 1 plus 2 minus k for all k. Any base may be used for the logarithm table. 53. Applications. A Nautilus shell displaying a logarithmic spiral. Logarithms have many applications inside and outside mathematics. Some of these occurrences are related to the notion of scale invariance. For example, each chamber of the shell of a Nautilus is an approximate copy of the next one, scaled by a constant factor. This gives rise to a logarithmic spiral. 54. Benford's law on the distribution of leading digits can also be explained by scale invariance. 55. Logarithms are also linked to self-similarity. For example, logarithms appear in the analysis of algorithms that solve a problem by dividing it into two similar smaller problems and patching their solutions. 56. The dimensions of self-similar geometric shapes, that is, shapes whose parts resemble the overall picture, are also based on logarithms. Logarithmic scales are useful for quantifying the relative change of a value as opposed to its absolute difference. Moreover, because the logarithmic function log x grows very slowly for large x, logarithmic scales are used to compress large-scale scientific data. Logarithms also occur in numerous scientific formulas, such as the Tsiolkovsky rocket equation, the Fensky equation, or the Nernst equation. Logarithmic scale. A logarithmic chart depicting the value of one gold mark in Papier marks during the German hyperinflation in the 1920s. Scientific quantities are often expressed as logarithms of other quantities, using a logarithmic scale. For example, the decibel is a unit of measurement associated with logarithmic scale quantities. It is based on the common logarithm of ratios, 10 times the common logarithm of a power ratio or 20 times the common logarithm of a voltage ratio. It is used to quantify the attenuation or amplification of electrical signals, 57, to describe power levels of sounds in acoustics, 58, and the absorbance of light in the fields of spectrometry and optics. The signal-to-noise ratio describing the amount of unwanted noise in relation to a meaningful signal is also measured in decibels. 59. In a similar vein, the peak signal-to-noise ratio is Scientific quantities are often expressed as logarithms of other quantities, using a logarithmic scale. For example, the decibel is a unit of measurement associated with logarithmic scale quantities. It is based on the common logarithm of ratios, 10 times the common logarithm of a power ratio or 20 times the common logarithm of a voltage ratio. It is used to quantify the attenuation or amplification of electrical signals, 57, to describe power levels of sounds in acoustics, 58, and the absorbance of light in the fields of spectrometry and optics. The signal-to-noise ratio describing the amount of unwanted noise in relation to a meaningful signal is also measured in decibels. 59. In a similar vein, the peak signal-to-noise ratio is commonly used to assess the quality of sound and image compression methods using the logarithm. 60. The strength of an earthquake is measured by taking the common logarithm of the energy emitted at the quake. This is used in the moment magnitude scale or the Richter magnitude scale. For example, a 5.0 earthquake releases 32 times, 101.5, and a 6.0 releases 1000 times, 103, the energy of a 4.0. 61. Apparent magnitude measures the brightness of stars logarithmically. 62. In chemistry, the negative of the decimal logarithm, the decimal collogarithm, is indicated by the letter p. 63. For instance, pH is the decimal collogarithm of the activity of hydronium ions, the form hydrogen ions H plus take in water. 64. The activity of hydronium ions in neutral water is 10-7 moles L-1, hence a pH of 7. Vinegar typically has a pH of about 3. The difference of 4 corresponds to a ratio of 104 of the activity, that is, vinegar's hydronium ion activity is about 10-3 moles L-1. Semilog log linear graphs use the logarithmic scale concept for visualization. One axis, typically the vertical one, is scaled logarithmically. For example, the chart at the right compresses the steep increase from 1 million to 1 trillion to the same space, on the vertical axis, as the increase from 1 to 1 million. In such graphs, exponential functions of the form f x equals a bx appear as straight lines with slope equal to the logarithm of b. Log graphs scale both axes logarithmically, which causes functions of the form f x equals a xk to be depicted as straight lines with slope equal to the exponent k. This is applied in visualizing and analyzing power laws. 65. Psychology. Logarithms occur in several laws describing human perception. 66-67. Hicks' law proposes a logarithmic relation between the time individuals take to choose an alternative and the number of choices they have. 68. Fitz's law predicts that the time required to rapidly move to a target area is a logarithmic function of the ratio between the distance to a target and the size of the target. 69. In psychophysics, the Weber-Fechner law proposes a logarithmic relationship between stimulus and sensation such as the actual versus the perceived weight of an item a person is carrying. 70. This law, however, is less realistic than more recent models, such as Stevens's power law. 71. Psychological studies found that individuals with little mathematics education tend to estimate quantities logarithmically, that is, they position a number on an unmarked line according to its logarithm, so that 10 is positioned. Psychological studies found that individuals with little mathematics education tend to estimate quantities logarithmically, that is, they position a number on an unmarked line according to its logarithm, so that 10 is positioned as close to 100 as 100 is to 1000. Increasing education shifts this to a linear estimate, positioning 1010 times as far away, in some circumstances, while logarithms are used when the numbers to be plotted are difficult to plot linearly. 73. Probability theory and statistics. 3 probability density functions PDF of random variables with log normal distributions. The location parameter mu, which is 0 for all 3 of the PDFs shown, is the mean of the logarithm of the random variable, not the mean of the variable itself. Distribution of first digits in percent, red bars in the population of the 237 countries of the world. Black dots indicate the distribution predicted by Benford's law. Logarithms arise in probability theory. The law of large numbers dictates that, for a fair coin, as the number of coin tosses increases to infinity, the observed proportion of heads approaches 1/2. The fluctuations of this proportion about 1/2. Logarithms arise. Distribution of first. Black dots indicate. Logarithms arise in probability theory. The law of large numbers dictates that, for a fair coin, as the number of coin tosses increases to infinity, the observed proportion of heads approaches 1/2. The fluctuations of this proportion about 1/2 are described by the law of the iterated logarithm. 74. Logarithms also occur in log normal distributions. When the logarithm of a random variable has a normal distribution, the variable is said to have a log normal distribution. 75. Log normal distributions are encountered in many fields, wherever a variable is formed as the product of many independent positive random variables, for example in the study of turbulence. 76. Logarithms are used for maximum likelihood estimation of parametric statistical models. For such a model, the likelihood function depends on at least one parameter that must be estimated. A maximum of the likelihood function occurs at the same parameter value as a maximum of the logarithm of the likelihood, the log likelihood, because the logarithm is an increasing function. The log likelihood is easier to maximize, especially for the multiplied likelihoods for independent random variables. 77. Benford's law describes the occurrence of digits in many data sets, such as heights of buildings. According to Benford's law, the probability that the first decimal digit of an item in the data sample is d, from 1 to 9 equals log 10 d plus 1 minus log 10 d regardless of the unit of measurement. 78. Thus, about 30% of the data can be expected to have 1 as first digit, 18% start with 2, etc. Auditors examine deviations from Benford's law to detect fraudulent accounting. 79. The logarithm transformation is a type of data transformation used to bring the empirical distribution closer to the assumed one. Computational complexity. Analysis of algorithms is a branch of computer science that studies the performance of algorithms, computer programs solving a certain problem. 80. Logarithms are valuable for describing algorithms that divide a problem into smaller ones, and join the solutions of the subproblems. 81. For example, to find a number in a sorted list, the binary search algorithm checks the middle entry and proceeds with the half before or after the middle entry if the number is still not found. This algorithm requires, on average, log2 n comparisons, where n is the list's length. 82. Similarly, the merge sort algorithm sorts an unsorted list by dividing the list into halves and sorting these first before merging the results. Merge sort algorithms typically require a time approximately proportional to n log n. 83. The base of the logarithm is not specified here, because the result only changes by a constant factor when another base is used. A constant factor is usually disregarded in the analysis of algorithms under the standard uniform cost model. 84. A function f(x) is said to grow logarithmically if f(x) is exactly or approximately proportional to the logarithm of x. Biological descriptions of organism growth, however, use this term for an exponential function. 85. For example, any natural number n can be represented in binary form in no more than log 2n plus 1 bit. In other words, the amount of memory needed to store n grows logarithmically with n. Entropy and chaos. Billiards on an oval billiard table. Two particles, starting at the center with an angle differing by 1 degree, take paths that diverge chaotically because of reflections at the boundary. Entropy is broadly a measure of the disorder of some system. In statistical thermodynamics, the entropy S of some physical system is defined as the sum is overall possible states I of the system in question, such as the positions of gas particles in a container. Moreover, pi is the probability that the state I is attained and k is the Boltzmann constant. Similarly, entropy in information theory measures the quantity of information. If a message recipient may expect any one of n possible messages with equal likelihood, then the amount of information conveyed by any one such message is quantified as log 2n bits. 86. Lyapunov exponents use logarithms to gauge the degree of chaoticity of a dynamical system. For example, for a particle moving on an oval billiard table, even small changes of the initial conditions result in very different paths of the particle. Such systems are chaotic in a deterministic way, because small measurement errors of the initial state predictably lead to largely different final states. 87. At least one Lyapunov exponent of a deterministically chaotic system is positive. Fractals. The Sierpinski triangle, at the right, is constructed by repeatedly replacing equilateral triangles by 3 smaller ones. Logarithms occur in definitions of the dimension of fractals. 88. Fractals are geometric objects that are self-similar in the sense that small parts reproduce, at least roughly, the entire global structure. The Sierpinski triangle pictured can be covered by 3 copies of itself, each having sides half the original length. This makes the Hausdorff dimension of this structure lane 3, lane 2 approximately equals 1.58. Another logarithm-based notion of dimension is obtained by counting the number of boxes needed to cover the fractal in question. Music. 4 different octaves shown on a linear scale, then shown on a logarithmic scale as the ear hears them. Logarithms are related to musical tones and intervals. In equal temperament tunings, the frequency ratio depends only on the interval between 2 tones, not on the specific frequency, or pitch, of the individual tones. In the 12-tone equal temperament tuning common in modern Western music, each octave doubling of frequency is broken into 12 equally spaced intervals called semitones. For example, if the note A has a frequency of 440 Hz, then the note B flat has a frequency of 466 Hz. The interval between A and B flat is a semitone, as is the one between B flat and B, frequency 493 Hz. Accordingly, the frequency ratios agree. Intervals between arbitrary pitches can be measured in octaves by taking the base 2 logarithm of the frequency ratio, can be measured in equally tempered semitones by taking the base minus 21/12 logarithm, 12 times the base 2 logarithm, or can be measured in cents, hundredths of a semitone, by taking the base minus 21/1200 logarithm, 1200 times the base 2 logarithm. The latter is used for finer encoding, as it is needed for finer measurements or non-equal temperaments. Number theory. Natural logarithms are closely linked to counting prime numbers 2, 3, 5, 7, 11, an important topic in number theory. For any integer x, the quantity of prime numbers less than or equal to x is denoted pi x. The prime number theorem asserts that pi x is approximately given by, in the sense that the ratio of pi x and that fraction approaches 1 when x tends to infinity. 90 as a consequence, the probability that a randomly chosen number between 1 and x is prime is inversely proportional to the number of decimal digits of x. A far better estimate of pi x is given by the offset logarithmic integral function Li x defined by the Riemann hypothesis, one of the oldest open mathematical conjectures, can be stated in terms of comparing pi x and Li x. 91. The Erdős-Kac theorem describing the number of distinct prime factors also involves the natural logarithm. The logarithm of n factorial, n, equals 1 to n, is given by. This can be used to obtain Stirling's formula, an approximation of n. For large n. 92. Generalizations. Complex logarithm. Polar form of z equals x plus iy. Both phi and phi, or arguments of z. All the complex numbers that solve the equation are called complex logarithms of z, when z is considered as a complex number. A complex number is commonly represented as z equals x plus iy, where x and y are real numbers and I is an imaginary unit, the square of which is minus 1. Such a number can be visualized by a point in the complex plane, as shown at the right. The polar form encodes a non-zero complex number z by its absolute value, that is, the positive, real distance r to the origin, and an angle between the real x-axis re and the line passing through both the origin and z. This angle is called the argument of z. The absolute value r of z is given by using the geometrical interpretation of sine and cosine and their periodicity in 2 pi, any complex number z may be denoted as for any integer number k. Evidently the argument of z is not uniquely specified. Both phi and phi equals phi plus 2k pi are valid arguments of z for all integers k, because adding 2k pi radians or k dot operator 360 degrees NB6 to phi corresponds to winding around the origin counterclockwise by k turns. The resulting complex number is always z, as illustrated at the right for k equals 1. One may select exactly one of the possible arguments of z as the so-called principal argument, denoted arg z with a capital A, by requiring phi to belong to one conveniently selected term, e.g. minus pi less than phi is less than or equal to pi 93, or 0 is less than or equal to phi less than 2 pi 94. The principal branch pi of the complex logarithm, log z. The black point at z equals 1 corresponds to absolute value 0 and brighter colors refer to bigger absolute values. The hue of the color encodes the argument of log z. Euler's formula connects the trigonometric functions sine and cosine to the complex exponential. Taking k such that phi plus 2k pi is within the defined interval for the principal arguments, then ac is called the principal value of the logarithm, denoted log z again with a capital L. The principal argument of any positive real number x is 0, hence log x is a real number and equals the real natural logarithm. However, the above formulas for logarithms of products and powers do not generalize to the principal value of the complex logarithm. 96. The illustration at the right depicts log z confining the arguments of z to the interval minus pi. This way the corresponding branch of the complex logarithm has discontinuities all along the negative real x-axis, which can be seen in the jump in the hue there. This discontinuity arises from jumping to the other boundary in the same branch, when crossing a boundary, i.e. not changing to the corresponding k value of the continuously neighboring branch. Such a locus is called a branch cut. Dropping the range restrictions on the argument makes the relations, argument of z, and consequently the logarithm of z, multi-valued functions. Inverses of other exponential functions. Exponentiation occurs in many areas of mathematics and its inverse function is often referred to as the logarithm. For example, the logarithm of a matrix is the multi-valued inverse function of the matrix exponential. 97. Another example is the p-adic logarithm, the inverse function of the p-adic exponential. Both are defined via Taylor series analogous to the real case. 98. In the context of differential geometry, the exponential map maps the tangent space at a point of a manifold to a neighborhood of that point. Its inverse is also called the logarithmic, or log map. 99. In the context of finite groups, exponentiation is given by repeatedly multiplying one group element b with itself. The discrete logarithm is the integer n solving the equation, where x is an element of the group. Carrying out the exponentiation can be done efficiently, but the discrete logarithm is believed to be very hard to calculate in some groups. This asymmetry has important applications in public key cryptography, such as for example in the Diffie-Hellman key exchange, a routine that allows secure exchanges of cryptographic keys over unsecured information channels. 100. Sex logarithm is related to the discrete logarithm in the multiplicative group of non-zero elements of a finite field. 101. Further logarithm-like inverse functions include the double logarithm lane x, the super-hyper-4 logarithm, a slight variation of which is called iterated logarithm in computer science, the Lambert W function, and the logit. They are the inverse functions of the double exponential function, tetration, of fw equals wu, 102, and of the logistic function, respectively. 103. Related concepts. From the perspective of group theory, the identity log CD equals log C plus log D expresses a group isomorphism between positive reals under multiplication and reals under addition. Logarithmic functions are the only continuous isomorphisms between these groups. 104. By means of that isomorphism, the Haar measure Lebesgue measure dx on the reals corresponds to the Haar measure dx x on the positive reals. 105. The non-negative reals not only have a multiplication, but also have addition, and form a summuring, called the probability summuring. This is in fact a semifield. The logarithm then takes multiplication to addition, log multiplication, and takes addition to log addition, log sum xb, giving an isomorphism of sumurings between the probability summuring and the log summuring. Logarithmic one forms df, f appear in complex analysis and algebraic geometry as differential forms with logarithmic poles. 106. The polylogarithm is the function defined by mathematics portal, arithmetic portal, chemistry portal. Moreover, Lit1 equals the Riemann zeta function zeta s. 107. Decimal derivative. In mathematics, the derivative is a fundamental tool that quantifies the sensitivity of change of a function's output with respect to its input. The derivative of a function of a single variable at a chosen input value, when it exists, is the slope of the tangent line to the graph of the function at that point. The tangent line is the best linear approximation of the function near that input value. For this reason, the derivative is often described as the instantaneous rate of change, the ratio of the instantaneous change in the dependent variable to that of the independent variable. 1. The process of finding a derivative is called differentiation. There are multiple different notations for differentiation, two of the most commonly used being Leibniz notation and prime notation. Leibniz notation, named after Gottfried Wilhelm Leibniz, is represented as the ratio of two differentials, whereas prime notation is written by adding a prime mark. Higher-order notations represent repeated differentiation, and they are usually denoted in Leibniz notation by adding superscripts to the differentials, and in prime notation by adding additional prime marks. The higher-order derivatives can be applied in physics. For example, while the first derivative of the position of a moving object with respect to time is the object's velocity, how the position changes as time advances, the second derivative is the object's acceleration, how the velocity changes as time advances. Derivatives can be generalized to functions of several real variables. In this generalization, the derivative is reinterpreted as a linear transformation whose graph is, after an appropriate translation, the best linear approximation to the graph of the original function. The Jacobian matrix is the matrix that represents this linear transformation with respect to the basis given by the choice of independent and dependent variables. It can be calculated in terms of the partial derivatives with respect to the independent variables. For a real-valued function of several variables, the Jacobian matrix reduces to the gradient vector. As a limit, a function of a real variable is differentiable at a point of its domain, if its domain contains an open interval containing, and the limit exists. 2. This means that, for every positive real number, there exists a positive real number such that, for every such that and then is defined, and where the vertical bars denote the absolute value. This is an example of the epsilon, delta definition of limit. 3. If the function is differentiable at, that is if the limit exists, then this limit is called the derivative of at. Multiple notations for the derivative exist. 4. The derivative of it can be denoted, ret is, prime of, or it can be denoted, ret is, the derivative of with respect to at, or, by or over at. See section notation below. If is a function that has a derivative at every point in its domain. The concept of a derivative can be extended to many other settings. The common thread is that the derivative of a function at a point serves as a linear approximation of the function at that point. An important generalization of the derivative concerns complex functions of complex variables, such as functions from a domain in the complex numbers 2. The notion of the derivative of such a function is obtained by replacing real variables with complex variables in the definition. 48. If is identified with by writing a complex number as then a differentiable function from to is certainly differentiable as a function from to in the sense that its partial derivatives all exist, but the converse is not true in general. The complex derivative only exists if the real derivative is complex linear, and this imposes relations between the partial derivatives called the Cauchy-Riemann equations. See holomorphic functions. 49. Another generalization concerns functions between differentiable or smooth manifolds. Intuitively speaking, such a manifold is a space that can be approximated near each point by a vector space called its tangent space. The prototypical example is a smooth surface in. The derivative or differential of a differentiable map between manifolds at a point in is then a linear map from the tangent space of it to the tangent space of at. The derivative function becomes a map between the tangent bundles of and. This definition is used in differential geometry. 50. Differentiation can also be defined for maps between vector space, such as Banach space, in which those generalizations are the Gateau derivative and the Frechet derivative. 51. One deficiency of the classical derivative is that very many functions are not differentiable. Nevertheless, there is a way of extending the notion of the derivative so that all continuous functions and many other functions can be differentiated using a concept known as the weak derivative. The idea is to embed the continuous functions in a larger space called the space of distributions and only require that a function is differentiable, on average. 52. Properties of the derivative have inspired the introduction and study of many similar objects in algebra and topology. An example is differential algebra. Here, it consists of the derivation of some topics in abstract algebra, such as rings, ideals, field, and so on. 53. The discrete equivalent of differentiation is finite differences. The study of differential calculus is unified with the calculus of finite differences in time-scale calculus. 54. The arithmetic derivative involves the function that is defined for the integers by the prime factorization. This is an analogy with the product rule. 55. Slope. In mathematics, the slope or gradient of a line is a number that describes the direction of the line on a plane. 1, often denoted by the letter m, slope is calculated as the ratio of the vertical change to the horizontal change, rise over run, between two distinct points on the line, giving the same number for any choice of points. Slope. The line may be physical, as set by a road surveyor, pictorial as in a diagram of a road or roof, or abstract. An application of the mathematical concept is found in the grade or gradient in geography and civil engineering. The steepness, incline, or grade of a line is the absolute value of its slope. Greater absolute value indicates a steeper line. The line trend is defined as follows. An increasing, or ascending, line goes up from left to right and has positive slope. A decreasing, or descending, line goes down from left to right and has negative slope. Special directions are: a square, diagonal, line has unit slope. A horizontal, line, the graph of a constant function, has zero slope. A vertical, line has undefined or infinite slope, see below. If 2 points of a road have altitudes y1 and y2, the rise is the difference y2 minus y1 equals delta y. Neglecting the Earth's curvature, if the 2 points have horizontal distance x1 and x2 from a fixed point, the run is x2 minus x1 equals delta x. The slope between the 2 points is the difference ratio. Through trigonometry, the slope m of a line is related to its angle of inclination theta by the tangent function. Thus, a 45 degrees rising line has slope m equals +1, and a 45 degrees falling line has slope m equals -1. Generalizing this, differential calculus defines the slope of a plane curve at a point as the slope of its tangent line at that point. When the curve is approximated by a series of points, the slope of the curve may be approximated by the slope of the secant line between two nearby points. When the curve is given as the graph of an algebraic expression, calculus gives formulas for the slope at each point. Slope is thus one of the central ideas of calculus and its applications to design. Notation. There seems to be no clear answer as to why the letter m is used for slope, but it first appears in English in O'Brien, 1844-2, who introduced the equation of a line as y equals mx plus b, and it can also be found in Todhunter, 1888-3, who wrote y equals mx plus c. 4. Definition. Slope illustrated for y equals 3/2 x minus 1. Click on to enlarge. Slope of a line in coordinate system, from fx equals -12x plus 2 to fx equals 12x plus 2. The slope of a line in the plane containing the x and y axes is generally represented by the letter m, 5, and is defined as the change in the y coordinate divided by the corresponding change in the x coordinate, between two distinct points on the line. This is described by the following equation. The Greek letter delta, is commonly used in mathematics to mean difference, or change. Given 2 points n, the change in from one to the other is run, while the change in is rise. Substituting both quantities into the above equation generates the formula. The formula fails for a vertical line, parallel to the axis, see division by 0, where the slope can be taken as infinite, so the slope of a vertical line is considered undefined. Examples. Suppose a line runs through 2 points, p equals 1, 2, and q equals 13, 8. By dividing the difference in coordinates by the difference in coordinates, one can obtain the slope of the line. Since the slope is positive, the direction of the line is increasing. Since m less than 1, the incline is not very steep, incline less than 45 degrees. As another example, consider a line which runs through the points 4, 15, and 3, 21. Then, the slope of the line is. Since the slope is negative, the direction of the line is decreasing. Since m greater than 1, this decline is fairly steep, decline greater than 45 degrees. Algebra and geometry. Slopes of parallel and perpendicular lines. If is a linear function of, then the coefficient of is the slope of the line created by plotting the function. Therefore, if the equation of the line is given in the form, then is the slope. This form of a line's equation is called the slope-intercept form, because can be interpreted as the y-intercept of the line, that is, the coordinate where the line intersects the axis. If the slope of a line and a point on the line are both known, then the equation of the line can be found using the point-slope formula. The slope of the line defined by the linear equation is dot. Two lines are parallel if and only if they are not the same line, coincident, and either their slopes are equal or they both are vertical and therefore both have undefined slopes. Two lines are perpendicular if the product of their slopes is -1 or one has a slope of 0, a horizontal line, and the other has an undefined slope, a vertical line. The angle theta between -90 degrees and 90 degrees that a line makes with the x-axis is related to the slope m as follows. And this is the inverse function of tangent. See inverse trigonometric functions. Examples. For example, consider a line running through points 2, 8, and 3, 20. This line has a slope, m, of 1. Can then write the line's equation, in point-slope form. Or the angle theta between -90 degrees and 90 degrees that this line makes with the x-axis is. Consider the two lines, y equals -3x plus 1 and y equals -3x minus 2. Both lines have slope m equals -3. They are not the same line, so they are parallel lines. Consider the two lines y equals -3x plus 1 and y equals x. 3 minus 2. The slope of the first line is m1 equals -3. The slope of the second line is m2 equals 1. 3. The product of these two slopes is -1. So these two lines are perpendicular. In statistics, the gradient of the least squares regression best fitting line for a given sample of data may be written as comma. This quantity m is called as the regression slope for the line. The quantity is Pearson's correlation coefficient, is the standard deviation of the y values and is the standard deviation of the x values. This may also be written as a ratio of covariances, 6. At each point, the derivative is the slope of a line that is tangent to the curve at that point. Note, the derivative at point A is positive where green and dashed dot, negative where red and dashed, and 0 where black and solid. The concept of a slope is central to differential calculus. For nonlinear functions, the rate of change varies along the curve. The derivative of the function at a point is the slope of the line tangent to the statistics. Calculus. Curve at the point and is thus equal to the rate of change of the function at that point. If we let delta x and delta y be the distances along the x and y axes, respectively between 2 points on a curve, then the slope given by the above definition, comma, is the slope of a secant line to the curve. For a line, the secant between any 2 points is the line itself, but this is not the case for any other type of curve. For example, the slope of the secant intersecting y equals x2 at 0, 0, and 3, 9 is 3. The slope of the tangent at x equals 3/2 is also 3 minus a consequence of the mean value theorem. By moving the 2 points closer together so that delta y and delta x decrease, the secant line more closely approximates the tangent line to the curve, and as such the slope of the secant approaches that of the tangent. Using differential calculus, we can determine the limit, or the value that delta y, delta x approaches as delta y and delta x get closer to 0. It follows that this limit is the exact slope of the tangent. If y is dependent on x, then it is sufficient to take the limit where only delta x approaches 0. Therefore, the slope of the tangent is the limit of delta y, delta x as delta x approaches 0, or dit dx. We call this limit the derivative. The value of the derivative at a specific point on the function provides us with the slope of the tangent at that precise location. For example, let y equals x2. A point on this function is -2, 4. The derivative of this function is dy dx equals 2x. So the slope of the line tangent to y at -2, 4 is 2. Operator -2 equals -4. The equation of this tangent line is y -4 equals -4x -2 or y equals -4x -4. Difference of slopes. The illusion of a paradox of area is dispelled by comparing slopes where blue and red triangles meet. An extension of the idea of angle follows from the difference of slopes. Consider the shear mapping. Then is mapped to the slope of is 0 and the slope of is. The shear mapping added a slope of. For 2 points on with slopes n, the image has slope increased by, but the difference of slopes is the same before and after the shear. This invariance of slope differences makes slope an angular invariant measure, on a par with circular angle, invariant under rotation, and hyperbolic angle, with invariance group of squeeze mappings. Roads and railways have both longitudinal slopes and cross slopes. Slope warning sign in the Netherlands. Slope warning sign in Poland. A1371 meter. Distance of a railroad with a 20 per mil slope. Czech Republic. Steam age railway gradient post. Indicating a slope in both directions at Meals railway station, United Kingdom. The concept of a slope or gradient is also used as a basis for developing other applications in mathematics. Gradient descent, a first-order iterative optimization algorithm for finding the minimum of a function. Gradient theorem, theorem that a line integral through a gradient field can be evaluated by evaluating the original scalar field at the endpoints of the curve. Gradient method, an algorithm to solve problems with search directions defined by the gradient of the function at the current point. Conjugate gradient method, an algorithm for the numerical solution of particular systems of linear equations. Nonlinear conjugate gradient method, generalizes the conjugate gradient method to nonlinear optimization. Stochastic gradient descent, iterative method for optimizing a differentiable objective function. Other uses. Slope. Permutation. In mathematics, a permutation of a set can mean one of two different things: an arrangement of its members in a sequence or linear order, or the act or process of changing the linear order of an ordered set. 1. According to the first meaning of permutation, each of the 6 rows is a different permutation of 3 distinct balls. An example of the first meaning is the 6 permutations orderings of the set 1, 2, 3 written as tuples. They are 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. Anagrams of a word whose letters are all different are also permutations. The letters are already ordered in the original word, and the anagram reorders them. The study of permutations of finite sets is an important topic in combinatorics and group theory. Permutations are used in almost every branch of mathematics and in many other fields of science. In computer science, they are used for analyzing sorting algorithms, in quantum physics, for describing states of particles, and in biology, for describing RNA sequences. The number of permutations of n distinct objects is n factorial, usually written as n, which means the product of all positive integers less than or equal to n. According to the second meaning, a permutation of a set S is defined as a bijection from S to itself. 2, 3, that is, it is a function from S to S for which every element occurs exactly once as an image value. Such a function is equivalent to the rearrangement of the elements of S in which each element I is replaced by the corresponding. For example, the permutation 3, 1, 2 is described by the function defined as dot. The collection of all permutations of a set form a group called the symmetric group of the set. The group operation is the composition of functions performing one rearrangement after the other, which results in another function rearrangement. The properties of permutations do not depend on the nature of the elements being permuted, only on their number, so one often considers the standard set. In elementary combinatorics, the k permutations, or partial permutations, are the ordered arrangements of k distinct elements selected from a set. When k is equal to the size of the set, these are the permutations in the previous sense. In the popular puzzle Rubik's Cube invented in 1974 by Erno Rubik, each turn of the puzzle faces creates a permutation of the surface colors. History. Permutation-like objects called hexagrams were used in China in the I Ching, Pinyin, Yi Jing as early as 1000 BC. In Greece, Plutarch wrote that Xenocrates of Chalcedon, 396 to 314 BC, discovered the number of different syllables possible in the Greek language. This would have been the first attempt on record to solve a difficult problem in permutations and combinations. 4. Al-Khalil, 717 to 786, an Arab mathematician and cryptographer, wrote the Book of Cryptographic Messages. It contains the first use of permutations and combinations, to list all possible Arabic words with and without vowels. 5. The rule to determine the number of permutations of n objects was known in Indian culture around 1150 AD. The Lilavati by the Indian mathematician Bhaskara II contains a passage that translates as follows. The product of multiplication of the arithmetical series beginning and increasing by unity and continued to the number of places, will be the variations of number with specific figures. 6. In 1677, Fabian Stedman described factorials when explaining the number of permutations of bells in change ringing. Starting from 2 bells, first, 2 must be admitted to be varied in 2 ways, which he illustrates by showing 1 2 and 2 1. 7. He then explains that with 3 bells there are 3 times 2 figures to be produced out of 3, which again is illustrated. His explanation involves, cast away 3, and 1.2 will remain, cast away 2, and 1.3 will remain, cast away 1, and 2.3 will remain. 8. He then moves on to 4 bells and repeats the casting away argument showing that there will be 4 different sets of 3. Effectively, this is a recursive process. He continues with 5 bells using the casting away method and tabulates the resulting 120 combinations. 9. At this point he gives up and remarks. Now the nature of these methods is such, that the changes on one number comprehends the changes on all lesser numbers. Insomuch that a complete peal of changes on one number seemeth to be formed by uniting of the complete peals on all lesser numbers into one entire body. 10. Stedman widens the consideration of permutations. He goes on to consider the number of permutations of the letters of the alphabet and of horses from a stable of 20. 11. A first case in which seemingly unrelated mathematical questions were studied with the help of permutations occurred around 1770, when Joseph Louis Lagrange, in the study of polynomial equations, observed that properties of the permutations of the roots of an equation are related to the possibilities to solve it. This line of work ultimately resulted, through the work of Évariste Galois, in Galois theory, which gives a complete description of what is possible and impossible with respect to solving polynomial equations in one unknown by radicals. In modern mathematics, there are many similar situations in which understanding a problem requires studying certain permutations related to it. The study of permutations as substitutions on n elements led to the notion of group as algebraic structure, through the works of Cauchy 1815 memoir. Permutations played an important role in the cryptanalysis of the Enigma machine, a cipher device used by Nazi Germany during World War II. In particular, one important property of permutations, namely, that 2 permutations are conjugate exactly when they have the same cycle type, was used by cryptologist Marian Rejewski to break the German Enigma cipher in turn of years 1932. 1933, 12-13. Definition. In mathematics texts it is customary to denote permutations using lowercase Greek letters. Commonly, either or are used. 14. A permutation can be defined as a bijection, an invertible mapping, a one-to-one and onto function from a set S to itself. The identity permutation is defined by for all elements, and can be denoted by the number, a by, or by a single one-cycle x. 15, 16. The set of all permutations of a set with n elements forms the symmetric group, where the group operation is composition of functions. Thus for 2 permutations and in the group, their product is defined by, composition is usually written without a dot or other sign. In general, composition of two permutations is not commutative. As a bijection from a set to itself, a permutation is a function that performs a rearrangement of a set, termed an active permutation or substitution. An older viewpoint sees a permutation as an ordered arrangement or list of all the elements of S, called a passive permutation. 17. According to this definition, all permutations in section 1 line notation are passive. This meaning is subtly distinct from how passive, i.e. alias, is used in active and passive transformation and elsewhere. 18. 19. Which would consider all permutations open to passive interpretation, regardless of whether they are in 1-line notation, 2-line notation, etc. A permutation can be decomposed into one or more disjoint cycles, which are the orbits of the cyclic group acting on the set S. A cycle is found by repeatedly applying the permutation to an element, where we assume a cycle consisting of k elements is called a k-cycle. See section cycle notation below. A fixed point of a permutation is an element x which is taken to itself, that is, forming a one-cycle. A permutation with no fixed points is called a derangement. A permutation exchanging two elements, a single two-cycle, and leaving the others fixed is called a transposition. Notations. Several notations are widely used to represent permutations conveniently. Cycle notation is a popular choice, as it is compact and shows the permutation structure clearly. This article will use cycle notation unless otherwise specified. Two-line notation. Cauchy's two-line notation 2021 lists the elements of S in the first row, and the image of each element below it in the second row. For example, the permutation of S equals 1, 2, 3, 4, 5, 6 given by the function can be written as. The elements of S may appear in any order in the first row, so this permutation could also be written. One-line notation. If there is a natural order for the elements of S, B, say, then one uses this for the first row of the two-line notation. Under this assumption, one may omit the first row and write the permutation in one-line notation as. That is, as an ordered arrangement of the elements of S. 22, 23. Care must be taken to distinguish one-line notation from the cycle notation described below. A common usage is to omit parentheses or other enclosing marks for one-line notation. Roth diagram for sigma I. 1, 2. This gives the most compact numbering permutations. One way to represent permutations of n things is by an integer n with 0 is less than or equal to n less than n, provided convenient methods are given to convert between the number and the representation of a permutation as an ordered arrangement sequence. This gives the most compact representation of arbitrary permutations, and in computing is particularly attractive when n is small enough that n can be held in a machine word. For 32-bit words this means n is less than or equal to 12, and for 64-bit words this means n is less than or equal to 20. The conversion can be done via the intermediate form of a sequence of numbers dn, dn-1, d2, d1, where d is a non-negative integer less than I. One may omit d1, as it is always 0, but its presence makes the subsequent conversion to a permutation easier to describe. The first step then is to simply express n in the factorial number system, which is just a particular mixed radix representation, where, for numbers less than n, the base is place values or multiplication factors, or successive digits are n-1, n-2, 2, 1. The second step interprets this sequence as a lemma code or almost equivalently as an inversion table. In the lemma code for a permutation sigma, the number dn represents the choice made for the first term sigma 1, the number dn-1 represents the choice made for the second term sigma 2 among the remaining n-1 elements of the set, and so forth. More precisely, each dn plus 1 minus I gives the number of remaining elements strictly less than the term sigma I. Since those remaining elements are bound to turn up as some permutations in computing. Later term sigma j, the digit dn plus 1 minus I counts the inversions I, j involving I as smaller index, the number of values j for which I less than j and sigma I greater than sigma j. The inversion table for sigma is quite similar, but here dn plus 1 minus k counts the number of inversions I, j, where k equals sigma j occurs as the smaller of the two values appearing in inverted order. 51. Both encodings can be visualized by an n by n Roth diagram, 52, named after Heinrich August Roth, in which dots at I, sigma I mark the entries of the permutation, and across at I, sigma j marks the inversion I, j. By the definition of inversions, across appears in any square that comes both before the dot j, sigma j in its column, and before the dot I, sigma I in its row. The lemma code lists the numbers of crosses in successive rows, while the inversion table lists the numbers of crosses in successive columns. It is just the lemma code for the inverse permutation, and vice versa. To effectively convert a lemma code dn, dn-1, d2, d1 into a permutation of an ordered set S, one can start with a list of the elements of S in increasing order, and for I increasing from 1 to n set sigma I to the element in the list that is preceded by dn plus 1 minus I other ones, and remove that element from the list. To convert an inversion table dn, dn-1, d2, d1 into the corresponding permutation, one can traverse the numbers from d1 to dn while inserting the elements of S from largest to smallest into an initially empty sequence. At the step using the number d from the inversion table, the element from S inserted into the sequence at the point where it is preceded by d elements already present. Alternatively, one could process the numbers from the inversion table and the elements of S both in the opposite order, starting with a row of n empty slots, and at each step place the element from S into the empty slot that is preceded by d other empty slots. Converting successive natural numbers to the factorial number system produces those sequences in lexicographic order, as is the case with any mixed radix number system, and further converting them to permutations preserves the lexicographic ordering, provided the lemma code interpretation is used. Using inversion tables, one gets a different ordering, where one starts by comparing permutations by the place of their entries 1 rather than by the value of their first entries. The sum of the numbers in the factorial number system representation gives the number of inversions of the permutation, and the parity of that sum gives the signature of the permutation. Moreover, the positions of the zeros in the inversion table give the values of left to right maxima of the permutation, in the example 6, 8, 9, while the positions of the zeros in the lemma code are the positions of the right to left minima, in the example positions of 4, 8, 9 of the values 1, 2, 5. This allows computing the distribution of such extrema among all permutations. A permutation with lemma code dn, dn-1, d2, d1 has an ascent n-I if and only if di is greater than or equal to di plus 1. Algorithms to generate permutations. In computing, it may be required to generate permutations of a given sequence of values. The methods best adapted to do this depend on whether one wants some randomly chosen permutations, or all permutations, and in the latter case if a specific ordering is required. Another question is whether possible equality among entries in the given sequence is to be taken into account. If so, one should only generate distinct multiset permutations of the sequence. An obvious way to generate permutations of n is to generate values for the lemma code, possibly using the factorial number system representation of integers up to n, and convert those into the corresponding permutations. However, the latter step, while straightforward, is hard to implement efficiently, because it requires n operations each of selection from a sequence and deletion from it, at an arbitrary position, of the obvious representations of the sequence as an array or a linked list. Both require, for different reasons, about n 2/4 operations to perform the conversion. With n likely to be rather small, especially if generation of all permutations is needed, that is not too much of a problem, but it turns out that both for random and for systematic generation there are simple alternatives that do considerably better. For this reason it does not seem useful, although certainly possible, to employ a special data structure that would allow performing the conversion from lemma code to permutation in n log n time. Random generation of permutations. For generating random permutations of a given sequence of n values, it makes no difference whether one applies a randomly selected permutation of n to the sequence, or chooses a random element from the set of distinct multiset permutations of the sequence. This is because, even though in case of repeated values there can be many distinct permutations of n that result in the same permuted sequence, the number of such permutations is the same for each possible result. Unlike for systematic generation, which becomes unfeasible for large n due to the growth of the number n, there is no reason to assume that n will be small for random generation. The basic idea to generate a random permutation is to generate at random one of the n sequences of integers d1, d2, dn satisfying 0 is less than or equal to d less than I. Since d1 is always 0 it may be omitted, and to convert it to a permutation through a bijective correspondence. For the latter correspondence one could interpret that reverse sequence is a lemma code, and this gives a generation method first published in 1938 by Ronald Fisher and Frank Yates. 53. While at the time computer implementation was not an issue, this method suffers from the difficulty sketched above to convert from lemma code to permutation efficiently. This can be remedied by using a different bijective correspondence. After using d to select an element among I remaining elements of the sequence, for decreasing values of I rather than removing the element and compacting the sequence by shifting down further elements one place, one swaps the element with the final remaining element. Thus the elements remaining for selection form a consecutive range at each point in time, even though they may not occur in the same order as they did in the original sequence. Applications. Permutations are used in the interleaver component of the error detection and correction algorithms, such as turbo codes. For example, 3GPP Long-Term Evolution Mobile Telecommunication Standard uses these ideas. See 3GPP Technical Specification 36.212/65. Such applications raise the question of fast generation of permutations satisfying certain desirable properties. One of the methods is based on the permutation polynomials. Also is a base for optimal hashing and unique permutation hashing. 66. Combination. In mathematics, a combination is a selection of items from a set that has distinct members, such that the order of selection does not matter, unlike permutations. For example, given 3 fruits, say an apple, an orange and a pear, there are 3 combinations of 2 that can be drawn from this set: an apple and a pear, an apple and an orange, or a pear and an orange. More formally, a k combination of a set S is a subset of k distinct elements of S, so 2 combinations are identical if and only if each combination has the same members. The arrangement of the members in each set does not matter. If the set has n elements, the number of k combinations, denoted by r, is equal to the binomial coefficient, which can be written using factorials as whenever, and which is 0 when. This formula can be derived from the fact that each k combination of a set S of n members has permutations, so or 1. The set of all k combinations of a set S is often denoted by. A combination is a selection of n things taken k at a time without repetition. To refer to combinations in which repetition is allowed, the terms k combination with repetition, k multiset, 2, or k selection, 3, are often used. For, if, in the above example, it were possible to have 2 of any one kind of fruit, there would be 3 more 2 selections, one with 2 apples, one with 2 oranges, and one with 2 pears. Although the set of 3 fruits was small enough to write a complete list of combinations, this becomes impractical as the size of the set increases. For example, a poker hand can be described as a 5 combination K equals 5 of cards from a 52 card deck N equals 52. The 5 cards of the hand are all distinct, and the order of cards in the hand does not matter. There are 2,598,960 such combinations, and the chance of drawing any one hand at random is 2,598,960th. Number of K combinations. 3-element subsets of a 5-element set. The number of K combinations from a given set S of n elements is often denoted in elementary combinatorics texts by, or by a variation such as, or even 5. The last form is standard in French, Romanian, Russian, and Chinese texts. Mathematics portal. A combination can also be thought of as a selection of 2 sets of items, those that go into the chosen bin and those that go into the unchosen bin. This can be generalized to any number of bins with the constraint that every item must go to exactly 1 bin. The number of ways to put objects into bins is given by the multinomial coefficient, where n is the number of items, m is the number of bins, and is the number of items that go into bin I. One way to see why this equation holds is to first number the objects arbitrarily from 1 to n and put the objects with numbers into the first bin in order, the objects with numbers into the second bin in order, and so on. There are distinct numberings, but many of them are equivalent, because only the set of items in a bin matters, not their order in it. Every combined permutation of each bin's contents produces an equivalent way of putting items into bins. As a result, every equivalence class consists of distinct numberings, and the number of equivalence classes is. The binomial coefficient is a special case where k items go into the chosen bin and the remaining items go into the unchosen bin. Probability. Probability is the branch of mathematics and statistics concerning events and numerical descriptions of how likely they are to occur. The probability of an event is a number between 0 and 1. The larger the probability, the more likely an event is to occur. Note 1, 2. A simple example is the tossing of a fair, unbiased coin. Since the coin is fair, the 2 outcomes, heads and tails, are both equally probable. The probability of heads equals the probability of tails, and since no other outcomes are possible, the probability of either heads or tails is 1/2, which could also be written as 0.5 or 50%. The probabilities of rolling several numbers using 2 dice. These concepts have been given an axiomatic mathematical formalization in probability theory, which is used widely in areas of study such as statistics, mathematics, science, finance, gambling, artificial intelligence, machine learning, computer science, game theory, and philosophy to, for example, draw inferences about the expected frequency of events. Probability theory is also used to describe the underlying mechanics and regularities of complex systems. 3. Interpretations. When dealing with random experiments, i.e., experiments that are random and well-defined, in a purely theoretical setting, like tossing a coin, probabilities can be numerically described by the number of desired outcomes, divided by the total number of all outcomes. This is referred to as theoretical probability, in contrast to empirical probability, dealing with probabilities in the context of real experiments. For example, tossing a coin twice will yield head-head, head-tail, tail-head, and tail-tail outcomes. The probability of getting an outcome of head-head is 1 out of 4 outcomes, or, in numerical terms, 1/4, 0.25 or 25%. However, when it comes to practical application, there are 2 major competing categories of probability interpretations, whose adherents hold different views about the fundamental nature of probability. Objectivists assign numbers to describe some objective or physical state of affairs. The most popular version of objective probability is frequentist probability, which claims that the probability of a random event denotes the relative frequency of occurrence of an experiment's outcome when the experiment is repeated indefinitely. This interpretation considers probability to be the relative frequency, in the long run, of outcomes. 4. A modification of this is propensity probability, which interprets probability as the tendency of some experiment to yield a certain outcome, even if it is performed only once. Subjectivists assign numbers for subjective probability, that is, as a degree of belief. 5. The degree of belief has been interpreted as the price at which you would buy or sell a bet that pays 1 unit of utility if E, 0 if not E, 6, although that interpretation is not universally agreed upon. 7. The most popular version of subjective probability is Bayesian probability, which includes expert knowledge as well as experimental data to produce probabilities. The expert knowledge is represented by some subjective prior probability distribution. These data are incorporated in a likelihood function. The product of the prior and the likelihood, when normalized, results in a posterior probability distribution that incorporates all the information known to date. 8. By Aumann's agreement theorem, Bayesian agents whose prior beliefs are similar will end up with similar posterior beliefs. However, sufficiently different priors can lead to different conclusions, regardless of how much information the agents share. 9. Etymology. The word probability derives from the Latin probabilitas, which can also mean probity, a measure of the authority of a witness in a legal case in Europe, and often correlated with a witness's nobility. In a sense, this differs much from the modern meaning of probability, which in contrast is a measure of the weight of empirical evidence, and is arrived at from inductive reasoning and statistical inference. 10. History. The scientific study of probability is a modern development of mathematics. Gambling shows that there has been an interest in quantifying the ideas of probability throughout history, but exact mathematical descriptions arose much later. There are reasons for the slow development of the mathematics of probability. Whereas games of chance provided the impetus for the mathematical study of probability, fundamental issues, note 2, are still obscured by superstitions. 11. According to Richard Jeffrey, before the middle of the 17th century, the term probable, Latin probabilis, meant approvable, and was applied in that sense, univocally, to opinion and to action. A probable action or opinion was one such as sensible people would undertake or hold, in the circumstances. 12. However, in legal contexts especially, probable could also apply to propositions for which there was good evidence. 13. Gerolamo Cardano, 16th century. Christian Huygens published one of the first books on probability, 17th century. The 16th century Italian polymath Gerolamo Cardano demonstrated the efficacy of defining odds as the ratio of favorable to unfavorable outcomes, which implies that the probability of an event is given by the ratio of favorable outcomes to the total number of possible outcomes. 14. Aside from the elementary work by Cardano, the doctrine of probabilities dates to the correspondence of Pierre de Fermat and Blaise Pascal, 1654. Christian Huygens, 1657, gave the earliest known scientific treatment of the subject. 15. Jacob Bernoulli's Ars Conjectandi Posthumus, 1713, and Abraham de Moivre's Doctrine of Chances, 1718, treated the subject as a branch of mathematics. 16. C. Ian Hacking's The Emergence of Probability, 10, and James Franklin's The Science of Conjecture, 17, for histories of the early development of the very concept of mathematical probability. The theory of errors may be traced back to Roger Coates's Opera Miscellanea Posthumus, 1722, but a memoir prepared by Thomas Simpson in 1755, printed 1756, first applied the theory to the discussion of errors of observation. 18. The reprint, 1757, of this memoir lays down the axioms that positive and negative errors are equally probable, and that certain assignable limits define the range of all errors. Simpson also discusses continuous errors and describes a probability curve. The first two laws of error that were proposed both originated with Pierre-Simon Laplace. The first law was published in 1774, and stated that the frequency of an error could be expressed as an exponential function of the numerical magnitude of the error, disregarding sign. The second law of error was proposed in 1778 by Laplace, and stated that the frequency of the error is an exponential function of the square of the error. 19. The second law of error is called the normal distribution or the Gauss law. It is difficult historically to attribute that law to Gauss, who in spite of his well-known precocity had probably not made this discovery before he was 2 years old. 19. Daniel Bernoulli, 1778, introduced the principle of the maximum product of the probabilities of a system of concurrent errors. Carl Friedrich Gauss. Adrien Marie Legendre, 1805, developed the method of least squares. Adrien Marie Legendre, 1805, developed the method of least squares, and introduced it in his Nouvelles méthodes pour la détermination des orbites des comètes, New Methods for Determining the Orbits of Comets. 20. In ignorance of Legendre's contribution, an Irish-American writer, Robert Adrain, editor of The Analyst, 1808, first deduced the law of facility of error. Theory. Like other theories, the theory of probability is a representation of its concepts in formal terms, that is, in terms that can be considered separately from their meaning. These formal terms are manipulated by the rules of mathematics and logic, and any results are interpreted or translated back into the problem domain. There have been at least two successful attempts to formalize probability, namely the Kolmogorov formulation and the Cox formulation. In Kolmogorov's formulation, see also probability space, sets are interpreted as events and probability as a measure on a class of sets. In Cox's theorem, probability is taken as a primitive, i.e., not further analyzed, and the emphasis is on constructing a consistent assignment of probability values to propositions. In both cases, the laws of probability are the same, except for technical details. There are other methods for quantifying uncertainty, such as the Dempster-Shafer theory or possibility theory, but those are essentially different and not compatible with the usually understood laws of probability. Applications. Probability theory is applied in everyday life in risk assessment and modeling. The insurance industry and markets use actuarial science to determine pricing and make trading decisions. Governments apply probabilistic methods in environmental regulation, entitlement analysis, and financial regulation. An example of the use of probability theory in equity trading is the effect of the perceived probability of any widespread Middle East conflict on oil prices, which have ripple effects in the economy as a whole. An assessment by a commodity trader that a war is more likely can send that commodities prices up or down, and signals other traders of that opinion. Accordingly, the probabilities are neither assessed independently nor necessarily rationally. The theory of behavioral finance emerged to describe the effect of such groupthink on pricing, on policy, and on peace and conflict. 24. In addition to financial assessment, probability can be used to analyze trends in biology, e.g., disease spread, as well as ecology, e.g., biological Punnett squares. 25. As with finance, risk assessment can be used as a statistical tool to calculate the likelihood of undesirable events occurring, and can assist with implementing protocols to avoid encountering such circumstances. Probability is used to design games of chance so that casinos can make a guaranteed profit, yet provide payouts to players that are frequent enough to encourage continued play. 26. Another significant application of probability theory in everyday life is reliability. Many applications. Probability theory is applied in everyday life in risk assessment and modeling. The insurance industry and markets use actuarial science to determine pricing and make trading decisions. Governments apply probabilistic methods in environmental regulation, entitlement analysis, and financial regulation. An example of the use of probability theory in equity trading is the effect of the perceived probability of any widespread Middle East conflict on oil prices, which have ripple effects in the economy as a whole. An assessment by a commodity trader that a war is more likely can send that commodities prices up or down, and signals other traders of that opinion. Accordingly, the probabilities are neither assessed independently nor necessarily rationally. The theory of behavioral finance emerged to describe the effect of such groupthink on pricing, on policy, and on peace and conflict. 24. In addition to financial assessment, probability can be used to analyze trends in biology, e.g., disease spread, as well as ecology, e.g., biological Punnett squares. 25. As with finance, risk assessment can be used as a statistical tool to calculate the likelihood of undesirable events occurring, and can assist with implementing protocols to avoid encountering such circumstances. Probability is used to design games of chance so that casinos can make a guaranteed profit, yet provide payouts to players that are frequent enough to encourage continued play. 26. Another significant application of probability theory in everyday life is reliability. Many consumer products, such as automobiles and consumer electronics, use reliability theory in product design to reduce the probability of failure. Failure probability may influence a manufacturer's decisions on a product's warranty. 27. The cache language model and other statistical language models that are used in natural language processing are also examples of applications of probability theory. Mathematical treatment. Calculation of probability, risk versus odds. Consider an experiment that can produce a number of results. The collection of all possible results is called the sample space of the experiment, sometimes denoted as. The power set of the sample space is formed by considering all different collections of possible results. For example, rolling a die can produce 6 possible results. One collection of possible results gives an odd number on the die. Thus, the subset 1, 3, 5 is an element of the power set of the sample space of dice rolls. These collections are called events. In this case, 1, 3, 5 is the event that the die falls on some odd number. If the results that actually occur fall in a given event, the event is said to have occurred. A probability is a way of assigning every event a value between 0 and 1, with the requirement that the event made up of all possible results. In our example, the event 1, 2, 3, 4, 5, 6 is assigned a value of 1. To qualify as a probability, the assignment of values must satisfy the requirement that for any collection of mutually exclusive events with no common results, such as the events 1, 6, 3, and 2, 4, the probability that at least one of the events will occur is given by the sum of the probabilities of all the individual events. 28. The probability of an event A is written as 29 or 30. This mathematical definition of probability can extend to infinite sample spaces, and even uncountable sample spaces, using the concept of a measure. The opposite or complement of an event A is the event not A, that is, the event of a not occurring, often denoted as, or, its probability is given by P not A equals 1 minus P A. 31. As an example, the chance of not rolling a 6 on a 6-sided die is 1, chance of rolling a 6 equals 1 minus 1. 6 equals 5. 6. For a more comprehensive treatment, see complementary event. If two events A and B occur on a single performance of an experiment, this is called the intersection or joint probability of A and B, denoted as independent events. If two events, A and B, are independent, then the joint probability is 29. Events A and B depicted as independent versus non-independent in space omega. For example, if two coins are flipped, then the chance of both being heads is 32. Mutually exclusive events. If either event A or event B can occur but never both simultaneously, then they are called mutually exclusive events. If two events are mutually exclusive, then the probability of both occurring is denoted as AND. If two events are mutually exclusive, then the probability of either occurring is denoted as AND. For example, the chance of rolling a 1 or 2 on a 6-sided die is not necessarily mutually exclusive events. If the events are not necessarily mutually exclusive, then rewritten. For example, when drawing a card from a deck of cards, the chance of getting a heart or a face card J, Q, K, or both, is since among the 52 cards of a deck, 13 are hearts, 12 are face cards, and 3 are both. Here the possibilities included in the 3 that are both are included in each of the 13 hearts, and the 12 face cards, but should only be counted once. This can be expanded further for multiple not necessarily mutually exclusive events. For 3 events, this proceeds as follows. It can be seen, then, that this pattern can be repeated for any number of events. Conditional probability. Conditional probability is the probability of some event A, given the occurrence of some other event B. Conditional probability is written, and is read, the probability of A, given B. It is defined B 33. If then is formally undefined by this expression. In this case, and are independent, since however, it is possible to define a conditional probability for some zero probability events, for example by using a sigma algebra of such events, such as those arising from a continuous random variable. 34. For example, in a bag of 2 red balls and 2 blue balls, 4 balls in total, the probability of taking a red ball is however, when taking a second ball, the probability of it being either a red ball or a blue ball depends on the ball previously taken. For example, if a red ball was taken, then the probability of picking a red ball again would be since only 1 red and 2 blue balls would have been remaining. And if a blue ball was taken previously, the probability of taking a red ball will be inverse probability. In probability theory and applications, Bayes' rule relates the odds of event to event before, prior to, and after posterior to conditioning on another event. The odds on to event is simply the ratio of the probabilities of the two events. When arbitrarily many events are of interest, not just two, the rule can be rephrased as posterior is proportional to prior times likelihood. Where the proportionality symbol means that the left-hand side is proportional to, i.e., equals a constant times, the right-hand side is varies,